I guess a couple of folks are still joining us, so let's get started. Today, I'm happy to introduce you guys Ram Tuvi. Ram received his bachelor and master degree in electrical and computer engineering from Ben Gurion University of the Negev, Israel, in 2010 and 2013. And then he received his PhD from the School of Electrical Engineering, Tel Aviv University, Israel, in 2018. While between 2011 and 14, he also worked as an electrical magnetic engineer at GOJI Food Solutions. In early 2019, Ram joined UTIG as a postdoc, and then he worked mainly in using compressed data to do high-resolution seismic imaging. He worked with Murnau, Doug, and me, and a couple of students within the exploration geophysics group, but he has a broad interest in a lot of research areas, including wave propagation theory, analytical and computational method in electrical magnetics, acoustic and seismology. And today, Ram will introducing us his newly developed imaging and inversion methods. So let's welcome Ram to give us a talk.
Can I start?
Yes, it's all yours, Ram.
Thank you. So before I begin, I just want to say that this is a joint work with both Zeyu and Dr. Minal Sen and Doug Foster, all from UTIG. And today I'm going to tell you how we are trying to impose sparsity on large-scale inverse problems. And I'll begin with introduction. And the first thing I would like to explain are what are inverse problems or inverse scattering problems. So these are class of methods in physics and mathematics that what we are trying to do is to estimate properties of an unknown object. Here in this right figure, it is denoted by O, from scatter data measurements. So a few examples for these parameters could be epsilon and mu for the electromagnetic problem. It might be the acoustic impedance in underwater acoustic, or the velocity in geophysical inversion. The way that this is done is plotted here. We have an incident wave that propagates through this object. Once it will propagate it, it will induce scatter fields. Then we record the scatter fields on two measurement planes. Here we have the reflected data, and here we have the transmitted data. And our goal will be to estimate the properties of O given the incident wave and the scattered data. In general, this reconstruction requires some diversity, which depends on the application. It could be illuminating the object by short pulse or several frequencies, or to illuminate it by several directions. This kind of inverse problem have wide range of application in several fields, including, for example, underwater acoustics. And here in this figure, we have sonar system that what we're trying to do is to map the seabed. And this is done by detecting the travel time between the incident and the received signal. Another application can come from material testing. As we can see in this left figure, we have a structure that we would like to find if there's some cracks or defects. So we go through it with a probe, and then we record the reflection over time, as we can see in this right figure. And from this measurement, we can know if it has any defects or cracks. Another application can come from target identifications. This is a SAR system. We also have some application in biomedical imaging, and here I give, for example, an ultrasound image. This is an important figure for me because it's ultrasound image of one of my kids, but this is how it looks today. Inverse problems are the opposite of the forward problems, where we already have the physical properties in hand, and we would like to calculate from them the data. Now, doing the reverse process, calculating the physical properties from the data by itself has some challenges from a mathematical point of view. And to understand it, We'll go back to 1903 to Jack Hadamard. He was a mathematician and he tried to come with some idea of what is a well-posed problem. Well-posed, it means that everything is as should be. And he said that for a well-posed problem, he described three criteria, basically. He said that for a well-posed problem, a solution should exist. And if we have a solution, it should be unique. And on top of it, it should be stable. It means that it will change continuously with the input. Inverse problems, on the other hand, are often ill-posed. And exact solutions are only limited to small-scale problems in terms of wavelengths. They're required to solve a large number of forward problems, which increase with the size of the model. So for large-scale problems, we have to use some physical approximations. Some highly used approximation are the physical optic approximation, the rate of approximation, or the Born approximation. In this talk, I will be focused on specific application of inverse problem, the geophysical inverse problem, or for seismology inversion, which is relatively large. The goal will be to estimate the Earth properties, and specifically we would like to find the velocity, the velocity components. It will be the structures and the composition of the background velocity from observed data. The way that this is done, we first have to collect the data as plotted in this right figure. So we have a source on the surface. Now we illuminate the subsurface. Once we have boundaries between two layers, we have a reflection, and then we record the reflected data over an array of receivers. There are several challenges for this problem. First, the Earth is considered to be a complicated medium to analyze wave propagation, and we need some higher order methods to analyze wave propagation even for one single point source, as we can see here. Second, the size of this problem leads to a large and complicated data set. Another problem comes from the data limitation. We only record the reflected data over a finite array of receivers. And in addition, geophysical inversion is often formulated as an iterative scheme, and they become expensive from a computational point of view. To demonstrate some of these difficulties, we consider a synthetic model, a 3D synthetic model, but it's really close to a true 3D one. It is called the C model. We have a cross-section of it. So we can see that it's relatively large. We have a large number of sources and receivers, and for each source, we have large data set. On top of it, we have very high velocity contrast, which leads to complex wave phenomena, and it could always take 1 year to build such a model. So all these challenges should be taken into account when we come to formulate an inversion algorithm. We would like it to be fast, we would like it to be accurate, and we would like it to be robust. To tackle these challenges, we must have some a priori knowledge on the wave data, its physical interpretation, and how to represent it correctly. And the basis for all these things is a deep understanding of the wave propagation mechanism. In our work, we're trying to achieve these goals by probing the medium using beam propagators. Beam propagators, or Gaussian beams, are given by this expression for simplicity in 2D, homogeneous medium, and plotted here are waves that propagate along specific axis in space. It's called the beam axis, and decay away from it. Sorry. Specifically, we are using here the beam summation method, which is a formula to analyze wave propagation using local propagators. Now, if we have a source distribution, as you can see here, the radiated field is given as superposition of beams. Each one of these beams is propagated locally as rays. We have this red ray and this blue ray. So they can be tracked locally even in a homogeneous medium, unlike the point sources that we saw before. But on the other hand, unlike rays, they're insensitive to geometrical optics translation regions, such as this green caustic. Now, if we have an observation point, this red observation point, only the beams that will pass near this point will contribute to the field there. So we can conclude that the main physics can be described using only few terms. And this approach, this formulation, provide us a way to convert the full wave problem to a ray-based strategy. And indeed, due to all these advantages, several beam-based seismic imaging, propagation, and inversion approaches has been proposed in the past. Still, most of these methods don't take into account the physical representation of the data, which will be very important for the inversion algorithm. To take the physical interpretation of the data, we use here a different approach. It is based on the ultra-wideband phase-space beam summation method. This is the mathematical background to our work, and I would like to review it in the next few slides. So this method is structured on theory of frames, and frame basically is over complete set of function. Here it is denoted by psi of x, and over complete means that we have more basis function than we actually need. Now, if we have a function u of x, it can be expanded as sum of the frame elements times expansion coefficient, as in Fourier series, for example. Now, since the frames are over complete, again, means that we have more basis function than we need, the expansion coefficients are not unique. We can also construct a dual frame function phi, and it can be shown that a minimal L2 norm set of coefficient, unique one, can be obtained by projecting the function u on the dual frame function phi, as done, for example, in Fourier transform. Some highly used frames are wavelets and window Fourier transform frame that are used here to construct the ultra-wideband phase-space beam summation method. So this method was structured originally in the context of window Fourier transform frame expansion of surface field. Here it is denoted by u naught of x. The frame elements are psi mu of x, where psi of x is typically localized window function. It will be a Gaussian. Mu is a 4 index, which defined in this right figure as spatial and spectral phase space lattice. Over this lattice, each one of these frame elements is localized around the blue points, and x bar and np bar. It defines the centers of the frame elements. In order that the set will be over complete, it is required that the unit cell area given by this criteria will be less than 2 pi. And if the frame is highly over complete, we can also construct the dual frame and approximate it analytically from the function psi, and it will have the same structures. Now we can use this method to expand the surface field. It is given by this expression. Here we have the frame elements and expansion coefficient. I will talk about them in a few moments. And to take the surface field and propagate it into the subsurface, and the final expression is given as sum of beam propagators with their weights. To calculate the beam propagators, we take the frame elements from the surface, from the discrete points, and propagate it into the subsurface, as you can see here. Here, for simplicity, they're plotted for homogeneous medium. So they are emanating from discrete point xm and propagate along straight lines for homogeneous medium defined by the initial array parameter Pn. The expansion coefficients or beam amplitude are given by this expression. So we can think about it as a Fourier transform with local window function. And so they give us some idea of what is the local radiation spectrum of the beams. And basically, this representation leads to a sparsity of the propagation algorithm, because it tells us which beams we should take into account when we come to propagate the field. And we will use this unique property in order to reduce the computational complexity of the inverse problem. So I remind you that the goal in this talk is to impose some sparsity on inverse problem. And for this, we'll need a fast and efficient imaging algorithm. So seismic imaging is a technique to find location of reflectors from data. Sometimes it's also migration, because what we are doing, we're migrating the data from the surface into the subsurface. In the seismic survey, the phase where we collect the data D is related to the medium reflectivity. The reflectivity will be the perturbation of the background velocity that we would like to find, to a propagation operator L. And in general, this relation is not linear. But if we have a good enough velocity model, we can linear this relation as D equals to L times M. Again, our goal to be to estimate M given the data and knowledge on the propagation operation L. The imaging condition is given by this expression. It is plotted in this figure. So what we have to do, we have to forward propagate the sources in time and backward propagate the receiver and cross correlate them. This is basically the imaging condition. The most accurate method is called reverse time migration. It is based on explicitly solving the wave equation. It becomes, on the other hand, computationally expensive when we have large number of sources and receivers. So we have somehow to improve the migration efficiency. And for this, we formulated a new imaging algorithm that utilizes the advantages of Gaussian beams in wave propagation. Still, unlike other Gaussian beam methods that I mentioned before that have been proposed in the past, we take into account the physical interpretation of the data, which will make our algorithm to reduce the computational complexity and better address this problem. To form our beam-based imaging approach, we'll go back to the imaging condition, the correlation between the sources and the backpropagated field. Now we expand both the incident and the backpropagated field using the ultra-wideband phase-space beam summation method. We plug both this expression into the imaging condition, and we obtain an imaging condition directly in the beam domain, this expression. And it comprises basically two terms. First, we have the imaging canal, and second, we have the beam transformation of the data. To understand this formula, let me please explore each one of these terms separately. I'll begin with the imaging canals, and as you can see here, they are given by multiplication of the source beam and the backpropagated beam. So from the previous slide, we can think about them as the correlation between the sources and the receiver beams. Now, since each one of these beams is localized wave, it means that it propagates along specific ray parameter. If we go to this right figure, we can think about this correlation as localized in space and oriented in specific direction. The beam transformation of the data is obtained by projecting the shot gathers D on two dual frames, and this is done over the surface. The red one corresponds to this to the incident beam, and the blue one corresponds to the backpropagated beam. A physical model for the beam data can be obtained under the Bone approximation, and under this region, we can think of the data as the local interaction between the imaging canals and the medium reflectivity. So we can say that the beam data extract the local sneds of reflection from specific area and in specific direction. So an outcome from this formula and this representation is a direct relation between the surface data and corresponding local scattering event over the subsurface. And I believe that it is very important and has several advantages for imaging. First, it leads to a sparse representation of the imaging algorithm. Since we calculated the data over the surface before doing the backpropagation phase, we can use this property in order to reduce the number of elements that needed to be backpropagated in order to form a good image. But second, it also leads to a target-oriented approach because we have a relation between specific data and specific targets. Next, I would like to explore these properties through numerical examples. And the first example is this simple model that is plotted in the left figure. It has two interfaces and a diffractor. On the right figure, we have the image that we got from our method. You can see that we managed to reconstruct both of the interfaces and the location of the diffractor. Again, this is a simple model. It is not relatively large. What is more important and to learn from this model is the relation from the data and specific images. And for this, let me please explore data correspond to two excitation. In the left figures, we have an excitation obtained from normal incident plane wave, and to generate the plane wave, we stack all the sources in phase. On the right figure, we have data correspond to a single beam that emanating from the middle of the surface and propagate in the normal direction. On the bottom figures, we have the beam representation or phase space representation of the scattering data. XM tell us at which location we detect the data, and PN tell us at which direction we detect the data. So you can see that over the phase space, the data is sparse. It's localized around 2 PN values. Each one of them corresponds to reflection for the first layer and for the second layer. For the plane wave excitation, we have a global excitation. It means that we illuminate all the subsurface. This is why we detect the data over all the receivers. On the other hand, for the beam excitation, we only illuminate the part of the layers within the beam width. This is why we detect the data over a small number of receivers. To further explore the relation between the data and the targets, we go back to the single beam excitation and its corresponding data set. Now we also plot the imaging kernels that correspond to the high values of the data, the first set and the second set. We plot the imaging kernels in the physical domain, the distance and the depth. And in black, we have the interfaces, the location of the interfaces. I remind you that according to our physical model, the imaging kernels, the correlation between the sources and the backpropagated beams should be oriented to the direction of the reflections from each one of these layers. So this one is oriented in this direction, so we take into account this reflectivity, and the second one take into account this reflectivity. To further explore it and demonstrate it, we use each one of these data sets separately in the imaging phase. And if we use only this data set, we manage to reconstruct only the first layer and the second layer as well. So an outcome is a direct relation between data and specific targets. And these results very much agree and verifies both our physical model and imaging formula. And they also show how well the phase space representation carrying out both the spatial and the spectral physical properties of the targets or the subsurface using only few elements. And again, this is an observation that can be obtained using only our method. After exploring this algorithm through the simple model, let's go to a more complicated model. This is the Marmousi model. This is some kind of benchmark model that was created around 1988. The goal of this model is to produce some complex seismic data, which also requires some advanced processing techniques to obtain a good image. Here we have 460 short and receivers. We have 80 frequency between 5 to 25 hertz, and the model size is relatively large. To explore the advantage of our algorithm to this model, we go again to the beam representation of the data, and we begin again with single beam excitation with these parameters. And if we go to the bottom left figure, it's emanating from the point x equals 1 with initial ray parameter of 0. On the top left figure, we have the phase space representation of the scatter data. So you can see again that even though we have way more complicated model, the data is still localized, is sparse. And what is nice here, that it is localized around the same phase space parameters, x equals 1 and p equals 0 as the incident wave. So we can conclude from the data by itself, without knowing what the velocity is and how the model looks like, that over this region, the medium behaves as stratified media along the z direction. And again, this is an observation that can be obtained by using only this method. In the right figure, we also compare this representation for data correspond to single point source and detected all over point receivers. The point source is located again at x equals 1. So what you can see that the data, unlike the beam data, is not localized, and we don't have any knowledge from which direction the data came from. We also plot the incident ray path and the incident beam propagator, and indeed they propagate along the z direction, which very much agree with our assumption from the data by itself that over this region, the medium behave as stratified media. Now, if we change the propagation direction, the data is still localized around the phase space, and it's localized around specific point and in specific slanting over the model. And this is the corresponding imaging kernel that also verify and agree with these assumptions. So we can say that the beam data filter out both and behave as a filter by spectral and spatial local filter of the subsurface. So we can use this property to image specific targets, but we can also use it to squeeze the data sets and reduce the number of calculations needed to form an image, and we will see it later. Now, these are the images result that we've got. This is the image that we got from the conventional methods, the point sources, and this is the image that we got from our method. So you can see that we managed to, they very much agree with each other. To calculate the beam propagators, we use numerical integration with 92 green functions, the exact solution for the green function for the medium. And because we don't have a good sampling interval over the surface, this is why we have this artifact on top for the conventional image, the conventional method, which reduce for our method. And I would like to take another moment on this point, because most of the Gaussian beam methods explored in the past, I used the advantage of ray tracing the beam spectral locality as fast solver. They take into account for each imaging point only the beams that highly pass near this point. Here we use the same advantage of the beam propagators, but we get some more accuracy because we construct the beam propagators using numerical integration with the green functions. Another advantage that obtained from our method is it can reduce the data size and number of calculation needed to form a good image. And this is done by going back to our physical model plotted here in the right. And I remind you that according to our physical model, the beam data correspond to local Snell's law reflection from specific area and in specific direction. In the left figure, we have the beam representation of the scatter data for single frequency, the full beam to beam. The axes are in the size of number of source beams and receiver beams. What it is nice to see here is how sparse the data is. Basically, we don't need the blue data points because they don't contain any physics, any reflection events. So when we come to form the image, we can neglect the corresponding image increments, again, because they don't contain any physics needed to form the image. This phase make our imaging algorithm to be sparser and easier to handle. And basically, this is what we are seeing here. This is the image that we got from the full data set. This is the image that we got from 10% of the data set. 10% of the data set, again, means that for each frequency, we threshold the top 10% of the data and used only the corresponding imaging kernels to calculate the image. And this is the image that we got from 5% of the data set. So you can see that we managed to reduce the number of calculations needed to form the image at each frequency, which of course will speed up the calculations. Without any, and if we compare these images, we didn't lose much details over the images. So we have a great tool to reduce the computational complexity, but what is nicer, that it is based on physical consideration of the subsurface. As we will see in the next few slides, this is very important property for inversion algorithms. So in the next few slides, I would like to talk about least square migration, which is very popular inversion algorithm in seismology. So the main drawback of migration is it only approximates the relation between the parameters, the medium parameters, and the data. It is not the exact inverse operation. So the corresponding image contains some errors due to the data limitation, some noise, and incorrect velocity model. We can reduce this error by formulating migration as least square inverse problem, which is called least square migration, or for simplicity, LSM. To form the LSM, let me recall again the Born approximation of the data. The data is given as L, the propagation operator, multiplying it by the medium reflectivity. The goal in LSM is to reduce the difference between the observed data, the data that we collect over field, and the predicted data, the data which was calculated using the Born approximation. Now, if we take the derivative with respect to the medium parameters, the reflectivity, the minimum is obtained using this expression, and it gives us a relation between the migrated image, the image obtained by the migration operation, the one that we saw before, the medium reflectivity through this Hessian matrix, which is L transpose L. The advantages of LSM over migration, that it reduced the migration artifacts, it gives us higher resolution, and it compensates for the true interpretation of the amplitudes of the image, since it is the inverse operator and not approximated operator. We'll see all these points in the next few slides. The main challenge comes from computational point of view, and roughly saying, my LSM, it is at least 10 times more computational expensive than migration. And this thing become big challenge when we have large, to construct both the propagation operator and the Hessian matrix, when we have large number of imaging points and sources and receivers. To overcome it, there are generally two implementations. The first is called image domain, where we're trying to approximate the Hessian. The second one is called data domain, where we don't construct the Hessian explicitly, we use some iterative scheme to overcome it. I'll begin reviewing the image domain, and I remind you that in image domain, we're explicitly constructing the Hessian, and then we apply the inverse of the Hessian on the migrated image, and we obtain the medium reflectivity. The main challenge, again, comes from constructing the Hessian, which can be huge for through large data set and physical model. So basically, to overcome it, there are two solution strategies. First, to approximate the Hessian using only few terms, and second, to use target-oriented approaches. And beam propagators as local propagators to doing it, because you can use the spectral locality of the beams. But still, most of this method missing the data interpretation, and as we saw before, it is very important to reduce the number of calculations needed to form a good image. So now we can use our imaging algorithm, and it allows us to build the Hessian matrix sparsely and relatively fast. To form our LSM algorithm, let me recall again to the migration, the imaging condition that we saw before, the beam imaging condition, and we sum over all frequencies. Here we have the imaging canals and the beam transformation of the data. Under the Bond approximation, the short gathers are obtained by multiplying the medium reflectivity by two green functions. This one corresponds to the receivers and the sources. Now we take this expression, we multiply it by two dual frames and invert the order of integration, and we obtain a beam representation of the Bond approximation, of the beam data, and it is obtained by applying a beam-based propagation operator on the medium reflectivity. And this propagation operator is basically, it have the kernels are the imaging kernels. And finally, we can approximate the medium reflectivity as applying the inverse of the Hessian on the migrated image. So the Hessian basically is L transpose L. And if we can construct sparsely the propagation operator, we can speed up the calculation of calculating the Hessian matrix. Getting into more details, this is how the propagation operator looks like. It has all the pairs of source and receiver beams and all the imaging points. Now we can use our previous results, the data and target relation, to construct it sparsely. And this localization comes from two points of view. First, for the imaging point of view, if we will go to this right figure, if we have here this imaging point, this region that we would like to image, we should take into account only pair of beams that highly overlap in this point. So we can go now to the propagation operator and delete from the propagation operator for each imaging point the imaging canal that don't contribute to form a good image there. But what is unique from our method comes from the data point of view. We know from the previous slides that the beam data correspond to local strengths of reflection from specific area and specific direction. And basically it tells us, if we look on the sparsity of the data, that we can threshold, before doing the multiplication, we can threshold from the propagation operator imaging canals with low amplitudes because they don't contain any physics or any data that will form a good image. So this is how we construct the propagation operator sparsely. both from the imaging point of view and from the data point of view. And for these 2 points help us to better address the problem of constructing the Hessian. Next, I would like to explore this approach through a numerical example. And I will go again to the Marmousi model and the reflectivity model. This is the beam representation of the data for signal frequency. We have all the source beam and the receiver beam. I remind you that each point is beam to beam scattering amplitude or imaging canal amplitude. In the left bottom figure, we have one row of the Hessian, and as expected, it is correspond to one imaging point. It is very localized. In the right figure, we have the imaging, the one row of the Hessian that we calculated from 10% of the data, the sparse one. And again, 10% of the data means that for each one of these 80 frequencies that we have, we threshold the highest amplitudes, and we use only the corresponding imaging kernels to construct the Hessian. So if you compare both of these Hessians, you can see that the sparse Hessian is not localized at the full Hessian. Still, it's localized around the same imaging point. You can see it here in the reflectivity model. It takes into account the reflectivity of the neighborhood of this imaging point. It is not blurred. It is not smeared. So we can conclude that we kept only the relevant imaging canals and the data from the full data set. Now, these are the images result that we've got. This is the true effectivity of the model. Here we have the image that we got from the full data set. Here we have the image that we got from 10% of the data set, 5% of the data set, again, 10 or 5% of the data set, we threshold the top 10% data set and use only the corresponding imaging canals to construct the imaging, both the image and the Hessian, and 1% of the data set. So if you compare these images to the true reflectivity, you can see they are very much aligned and agree with the reflectivity of the model. What is nicer to see that we managed to reduce the calculation time from the full data set or the full Hessian from days up to 2 hours with 1% of the data set. And again, these results show how well we filter out the data and kept only the relevant data from the full data set in order to form a good image. Because even for 1% of the data set, we managed to reconstruct most of the reflection events, even though we reduced the computational complexity from days to hours. And again, these results show how well the phase space, our unique representation, carrying out both and filter out both the physical properties of the data needed to form a good image. A different approach is to use data domain formulation, and in data domain, we don't explicitly construct the Hessian. We use iterative scheme to reduce the error. These formulations are based on local gradient search. The iterative scheme is given here and summarized here. We begin with the observed data, we backpropagate it, and we calculate a reflectivity model. Then we calculate in the next step the gradient. This is done by backpropagating the difference between the observed and the predicted data. Then we recalculate the new data. We calculate the step length. We update the data residual and the model, and then we check the error. So we will continue doing it until we have a good enough accuracy. The main drawback and the most time-consuming phase come from these 2 phases, where we have to recalculate the wave equation. So Gaussian beam method try to overcome this problem using the spectral locality of the beams. It means, again, for each imaging point, they take into account only the beam that passed near this point. Still, they're required to recalculate the ray parameter at each iteration. In our approach, we can use, again, the spectral locality of the beams, but on top of it, we use a small number of wave equations to calculate the beam propagators. It gives us more accuracy, but we can also store them in the computer memory, so we don't have to recalculate the wave equation at each iteration. And in addition, as we saw before, we can threshold those past the data sets needed to form the image. And this is why at each iteration, we do it faster. So we go back to the Marmousi model to demonstrate these properties. This is the reflectivity model. This is the image that we got from the migration operation. And if we compare these images, You can see that we managed to reconstruct most of the subsurface, but these parts are not well recovered. In the bottom figure, the left bottom figure, we have the image that we got from our LSM image, and you can see that we managed to improve the medium, and you can see how it agreed well with the reflectivity. We also plot these results over line. In black, we have the true reflectivity of the model. In blue, we have the reflectivity that we got from our LSM method. You can see how good the amplitude match. And in red, you can see that the image that we've got, the results, I'm sorry, that we've got from the migration operation. We can further reduce the number of sources and receiver needed to form a good image. I remind you that LSM is a linear approach. We don't need to recalculate the response of the background or to update the background at each iteration. But on the other hand, the same consideration can be done for higher order methods, for nonlinear inversion, where you need to recalculate the velocity and recalculate the green functions. So it will be very important to reduce the number of green functions needed to form a good image. So these are the images that we've got from the migration operation from reduced number of green function, here 46 green function, before we had 92, and 23 green function. So we can see that the migrated images are not as good as before, but if we form again our LSM approach, we manage to get way better images. And finally, we can also compress the data size needed for imaging. And this is the image that we got from only 20% of the data, 20% of each iteration. And of course, it reduced the number of calculations needed to form at each frequency to 20%. And this is the LSM image. And you can see how well it agrees with the reflectivity of the model. We also plot the result over line. And in black again, we have the true reflectivity. In blue, we have the reflectivity that we've got from the full data set. And in red, we got the reflectivity that we got from the sparse data set. To conclude this talk, we saw a new approach of imposing sparsity on large-scale inverse problem. The method is based on transforming the full wave problem into local domain, the beam domain. We saw that this new representation better addressed this problem. It gives us fast, accurate, and more robust algorithm that can be implemented to nonlinear inversion. So what can be further done using these approaches? First, to extend it to additional analytical and semi-analytical models to anisotropic media. All the results that we saw before are acoustic waves, maybe layered media that has some application in underwater acoustic, and medium with losses. Another extension can be done by using this method as a physical method for higher order computational method. We know that the beam data, as we saw before, capture the physical properties of the medium using only few elements. So we might use this data set as an input for machine learning algorithm, and to overcome the most time-consuming phase, the backpropagation, and to predict the targets from the data by itself. Another thing that we can do is to reduce the number of shots needed to form a good image, as we can see in this right figure. The way that it is done today, for each shot, we calculate the shot effectiveness. It is done by some kind of clustering methods, but still they're required to solve large number of wave equations. So we try to come with some idea to predict the most contributing shots from the beam data by itself. And finally, maybe the main challenge with this method is to extend them to nonlinear inversion algorithms. They have application in both, of course, seismic inversion, but in an electromagnetic inverse problem or in biomedical imaging, where the main challenge comes from the size of the model, the complexity of the medium, while the current implementation are limited to small-scale problems. For large-scale problem, it's desired to have an efficient, a target-oriented, and very fast solver. And I think that the results that I showed today have great potential doing it. Finally, I would like to thank you for your listening.
All right. Thanks, Ren, for the very nice talk. If there's any questions from the audience, please raise your hand, or you can type the question into the chat box. Hey, Gail, please go ahead.
Yeah, so I had a question. So right now, you're saying this only works for small scale. Have you tried applying this to any data sets that we might have at the Institute?
It's not that I applied it to small scales. It's synthetic data, but this is something that indeed I would like to do, and Zeyu really recommended to me to doing it. I think that this is the next phase, because we begin with some bone synthetic data, and then we applied it on synthetic data to learn what is the limitation of the method. And of course, the next step will be to apply it into real data set. And I would be happy to collaborate with anyone that would like to do it.
Yeah, no, I mean, it'd be exciting to see how it compares with some of the other methods that we've used.
Yeah, I think Gail has a pretty good point. Actually, we are thinking to utilize some of the data sets from the axial volcano, but we haven't, executed the plan because we need to talk with Adrian first. But I think this is on the to-do list.
I have to say that I don't say it oftenly, but I really believe that it should work, because basically the beam methods have been applied in the past for true data set. The most contributing, or the most, I would say, the work of Ross Hill, if you know him, was like he was working in industry on true data set. And we showed him our result. He was really positive about them. So I'm pretty sure that they should work. But because we use basically the same consideration, but on top of it, we use a sparse or compressed data set in order to form an image. So this should speed up the calculation. I have to say that if we are considering iterative scheme, maybe in the first iteration, we don't have a good enough results as the previous ones, but we will get to the good results faster than other methods.
Any other questions from the audience?
So Ram, in your conclusion, you said that it's applicable to higher order problems. What could you explain what your thinking there is?
So I think that first, the same consideration should work for FWI or any optimization method, because in optimization methods, for example, in the electromagnetic, for example, or in biomedical imaging, they try to apply FWI for this for biomedical imaging or for electromagnetic problems. But the main drawback that they have to resolve the wave equation at each iteration. And it becomes very slow, especially for real-time or a real-time application. And I think we can use optimization methods in order to speed up first the forward calculations and the number of calculations needed to form the image. So they could really speed up these optimization methods. And this is how I see it.
Thanks, that's interesting.
Mm-hmm.
Ram, I have a question. So you mentioned the medical imaging or biological imaging.
Mm-hmm.
In the ultrasound applications, what I learned is that they're using high frequency wave, and that is very sensitive to the attenuation effect in the body, human body, or any materials. So how in your case, how can you handle that effect, or what kind of difficulty or what application do you think you can utilize your method in the medical imaging?
So I think the main drawback of today of biomedical imaging come from CT scans or from MRI. So for CT scan, of course, it is not safe way to do, and MRI requires to scan the body over a machine, and sometimes there's several people they can't use it, and you should have this machine, which is very expensive. On the other hand, it's become very popular today to use FWL because it gives us some higher resolution for the imaging of the brain. So basically, if you would like to speed up the calculations, you can use our method or to use the sparse representation of the data to do it faster. And this is how I think that it can be used for biomedical imaging, because you have to come with some faster and I would say not expensive solution, which compared for MRI or CT scans.
Okay, so in the FWI application for the biomedical imaging, how would that? So you mentioned that if you use FWI, the accuracy or the resolution will be higher than the traditional method.
Yeah, it is higher. It is already something that has been and it has been done and proved.
Okay.
Because the regular, I would say, ultrasound image for the brain, or it has lower resolution than MRI. But on the other hand, MRI is expensive from both computational time. It's required to stay with no moving for a long time. And it is something that not all people can do, and it requires to buy this machine, which it could be very expensive. And I can say that in Israel, where I came from, there are not many MRI machines, so you can wait several months to do an MRI scan.
Okay. Hey, Doug.
Can you see an application or extend this to surface waves that might be more applicable to global seismology?
I have to say that I have less experience with that, but I would love to see and discuss it with you.
Thank you.
Okay. Any more questions from the audience? All right. If no more questions, let's thank our speaker again. And thank you all for joining us today. Enjoy your weekends, and in the meantime, stay safe. All right.
Thank you.
See you guys.
Bye.
Thank you, Charles.
Bye.